Over the past couple of months, I've done quite a couple of videos where I have a closer look at the semiconductor frequency boosting technologies. Typically, it's not that complicated as there's a clear starting point and then several iterations that improve on that technology. For AMD, that's not quite the case. Our story can either start in 2015 when AMD came up with the adaptive voltage frequency scaling technology, or we can start in 2001 when ATI introduced the PowerPlay technology. While I would love to do a deep dive in PowerPlay going all the way back to 2001, I think for this video guide, maybe the best point to start off is in 2010 when AMD introduced their first AMD-branded graphics card. In 2006, AMD acquired ADI Technology, a Canadian GPU semiconductor graphics company, for about $5.4 billion. The acquisition was part of AMD's plan to change how CPUs are built. In AMD's vision, the future of the CPU was not just a chip, but an SoC or system on a chip. The SoC would integrate functions like I/O and graphics alongside the CPU. In addition to developing a true system on chip, acquiring ATI technology also brought AMD to the forefront of the discrete graphics market. AMD continued to market their discrete graphics under the ATI Technologies brand until the Radeon HD 5000 series launched in 2009. On October 22, 2010, AMD launched its very first AMD-branded discrete graphics card in the form of the AMD Radeon HD 6870. Less than 2 months later, AMD launched the new TeraScale 3 GPU architecture and Northern Islands product family with AMD Radeon HD 6970 as the flagship product. Among the many novelties, AMD introduced a new dynamic voltage frequency scaling technology, DVFS, called AMD PowerTune as the successor to the acquired ATI PowerPlay technology. ATI introduced the PowerPlay technology in 2001 as a form of dynamic power management, or DPM, for their mobile graphics. In short, PowerPlay consisted of 3 fixed power states, each defined by a specific power, voltage, and frequency for the GPU. As the workload shifts from low to heavy and back, the power state adjusts accordingly. This ensures maximum performance when needed for heavy workloads and minimum power usage when there are no workloads at all. Traditionally, the power states have fixed voltage and frequency. However, workloads can vary significantly in how they use the GPU. As a result, GPU power draw in the highest performance state can differ wildly depending on the specific application. If we had an unlimited power budget, this would be no problem. But unfortunately, we're always power limited. Semiconductor companies like AMD address this challenge by utilizing a TDP or thermal design power limit. The TDP captures the maximum power a product can reliably operate at within the warranty period. The voltage and clock speeds selected for the highest power state are therefore limited by 1. The worst case scenario for peak power use, 2. The maximum voltage that fits within the power budget, and 3. The highest frequency that the GPU can run given that voltage. These 3 compounding worst case scenarios result in a very conservative configuration for maximum performance. Furthermore, very few real-world applications would ever meet those worst case scenarios. So the result is that in the real world, you lose a lot of potential performance. A 2010 white paper lays out the argument for the AMD PowerTune technology. PowerTune aims to deliver higher performance optimized to the GPU's power limits by dynamically adjusting the clock during runtime based on an internally calculated GPU power assessment. By dynamically managing the GPU clock frequency based on the GPU's proximity to the rated TDP, the technology enables higher clock speeds in the highest power state. So, the AMD PowerTune technology allows for dynamic frequency adjustment to fit within the TDP envelope, rather than restricting the GPU's frequency by a worst-case power expectation. Essentially, AMD employs several inferred power states with lower GPU frequencies between the highest P state and the intermediate P state. To make the inferred states as effective as possible,
It's essential to have high granularity in terms of frequency. The result is substantially higher frequencies and resulting performance in typical workloads like gaming while staying within the power budget.
Another feature that AMD added to its portfolio when it acquired ADI Technologies in 2005 was Overdrive. Overdrive was a new feature that was added to the ATI Catalyst 3.8 software alongside the release of the ATI Radeon 9800 series graphics cards.
Its function was pretty simple. If you enable overdrive, then the GPU frequency would increase from 412 MHz to 419 MHz if the GPU temperature is below 56 degrees Celsius. By the third iteration of the overdrive feature, ATI had enabled advanced performance tuning tools such as manual GPU and memory overclocking and even an automatic overclocking function. The overdrive feature would continue to live within the ATI Catalyst software suite with the same overclocking toolkit even after AMD's acquisition and the introduction of PowerTune technology in 2010. With the transition from PowerPlay to PowerTune, the overdrive overclocking knobs also received a minor overhaul. Whereas we used to have just two options to control the GPU clock and memory clock, from the Radeon HD 6000 series onwards, we have three settings: high performance GPU clock, high performance memory clock, and power control. The high performance GPU and memory clock represents the maximum clock frequencies the card is allowed to run at in the highest power state. This maximum frequency is still constrained by the power usage and may decrease if the current power exceeds the TDP. The power control knob allows us to adjust the maximum power usage in the highest performance state.
The last topic we must tackle before moving forward is the VBIOS. The VBIOS is essentially the BIOS on the graphics card, and it contains all the information required to boot up your graphics card.
The VBIOS often contains multiple modules which provides information about the graphics card or defines certain specifications. On AMD graphics cards, a specific module called PowerPlay Info contains all information related to the performance specification, such as the frequency and voltage for each DPM state, power and thermal limits, and fan speed configuration. We can find this module by extracting the VBIOS ROM. In the past, enthusiasts could edit the PowerPlay module and flash a VBIOS with custom settings to their graphics card. Nowadays, AMD digitally signs the VBIOS firmware. While it's still possible to extract the VBIOS and make modifications, without the ability to correctly digitally sign, the card will not boot up with a custom VBIOS. The graphics software has a PowerPlay driver component that reads the information from the VBIOS and configures the appropriate frequency, voltage, and fan speed configuration. And users could override the PowerPlay driver configuration using a soft PowerPlay registry entry. This registry entry is essentially a direct copy of the VBIOS module.
We'll touch on this topic a couple of times as it's particularly relevant for overclocking.
In January 2012, AMD launched the brand new Graphics Core Next GPU architecture and the Southern Islands product family with the AMD Radeon HD 7970 as the flagship product. 6 months later, on June 22, 2012, AMD introduced the AMD Radeon HD 7970 GHz edition graphics card in response to the launch of the NVIDIA GeForce GTX 680. As the name already suggests, the GHz edition was a higher clock version of the same 7970 launched 6 months earlier, but with a twist. There's a boost. AMD PowerTune technology with Boost, or PT Boost, introduces a new approach to maximizing out-of-the-box frequency and performance. The idea is pretty simple. AMD adds a boost P state on top of the previous highest P state. This additional P state allows for extra voltage and thus higher operating frequency. The boost P state works the same as other P states, as the internal power usage estimate primarily drives it. However, on top of that, AMD also adds temperature into the equation. AMD calls this digital temperature estimation, or DTE. AMD estimates the actual junction temperature using DTE instead of assuming the GPU is operating at the worst case junction temperature. On March 22, 2013, AMD launched the second generation graphics core next GPU architecture and the Sea Islands product family, with the Radeon HD 7790 as initial flagship product and the Radeon R9 290X as the later flagship product. AMD also introduced an enhanced version of PowerTune technology alongside many new improvements. Until now, AMD's technology offered 4 distinct dynamic power management states: boost state, high state, intermediate state, and low state. Several inferred states had slightly lower frequency but identical voltage as the master P state between the boost state and the intermediate state. While this implementation offered AMD many improvements in performance per watt and power efficiency, a key drawback was that these inferred states didn't adjust the operating voltage. However, as we all know, voltage is a crucial driver for power usage. The enhanced version of PowerTune doubled the amount of DPM states from 4 to 8. That also effectively doubled the clock voltage pairings and, in theory, should offer more significant power efficiency gains. However, AMD did not continue with the inferred states, which reduced the clock frequency granularity. Implementing more fine-grained power states is not that straightforward. First, you need to switch as quickly as possible between states to optimize for power efficiency. Second, you also need fast and accurate telemetry to enable more rapid switching. The enhanced PowerTune technology relies on the AMD SVI2 interface. SVI stands for Serial VID Interface and is an AMD-designed VR controller interface. The second generation SVI was initially released in early 2010 and provides a range of features including greater granularity in voltage selection, faster data rate, and telemetry functions. As a result, the enhanced PowerTune architecture includes 3 main inputs: hardware temperature monitoring, internal power and current estimates, and external VRM telemetry inputs. The SMU evaluates these inputs and decides which is the optimal DPM state for the GPU. The DPM state then determines the clock frequency, the voltage, and the fan control setting. As the GPU will switch faster between states, it's also more challenging to know at what frequency the GPU is operating. To accurately communicate the actual operating frequency to the end user, AMD introduced the effective clock. The effective clock is essentially the average clock frequency over a period of 50 milliseconds. The final aspect of the enhanced PowerTune is exposing the ability to adjust the GPU target temperature.
Before continuing with the AMD GPU frequency boost technology, let's make a small sidestep to the CPU side of things. In 2014, AMD launched their 25x20 initiative, which was a bold initiative to improve the power efficiency by 25x by the year 2020 in their mobile processors. They proudly announced having exceeded this target by achieving 31.7 times energy efficiency 6 years later. To incredibly oversimplify this challenge, there are 2 main ways how AMD got around doing this. 1, increase the compute performance for a given power budget through architectural innovation of their CPUs and GPUs integrated into the APUs. 2, decrease the power use for a given compute performance by innovations in real-time power management and silicon-level power optimizations. A first stepping stone in that direction was the introduction of voltage adaptive operation and adaptive voltage frequency scaling technologies in Carrizo. Carrizo is a 15-watt 28nm APU, part of the 3rd generation bulldozer-based microarchitecture codenamed Steamroller. Importantly, it was the first AMD product to introduce AVFS for CPU and GPU cores. In a modern processor, everything starts with the power delivered from the 12-volt DC rail of the power supply across the motherboard to a voltage regulator. The voltage regulator then converts it to about 1 volt. That 1 volt is then delivered via the motherboard to the processor socket, where it gets transferred via the socket pins to the processor package and ultimately ends up at the processor die. The voltage to the processor is not constant. The processor uses higher voltage when it boosts to a higher frequency in response to a demanding workload. Conversely, the processor uses lower voltage when in an idle state.
switching from high to low load and vice versa causes significant voltage fluctuations. This phenomenon is commonly known as a voltage droop. The problem with voltage droops is very well known to overclockers. A voltage droop can cause the operating voltage to fall too low, causing system instability. In the past, chip designers would address this issue by supplying 10 to 15% excess voltage to ensure the chip always has sufficient voltage even after a significant voltage droop.
Unfortunately, power scales proportionally to the square of voltage. That means for every 10% increase in voltage, you'll have a 21% increase in power consumption. Clearly, if you're trying to improve power efficiency by 25x, looking at the voltage and having a tight grip on the voltage is an important topic. Carrizo addresses this with two technologies:
clock stretching and adaptive voltage frequency scaling. Clock stretching is something any Ryzen CPU overclocker already knows very well. To keep it short, a circuit on the processor tracks the operating voltage and compares the average voltage to the droops. If the actual voltage drops below the average, the processor briefly reduces the frequency accordingly. The system can respond in nanoseconds, which means typically the user would not notice the temporary reductions in clock frequency. If clock stretching is active for an extended period, you would see a significant decrease in performance. Adaptive voltage frequency scaling is a technology that implements many silicon speed capability sensors and voltage sensors in addition to the already present temperature and power sensors. Silicon speed capability means the maximum operating frequency of a chip. AVFS enables setting the optimal frequency for a given power or performance level across process, voltage, and temperature ranges.
More importantly, this technology can maximize the performance for a golden sample as well as a total dud of a chip. In other words, your golden sample will be able to clock a little bit higher than your total dud of a chip. Does this sound familiar, Ryzen overclockers? Anyway, now that we understand the purpose of clock stretching and AVFS, let's return to the GPU side of AMD's business.
While AMD first introduced the third generation GCN architecture with the Volcanic Islands product family in 2014, it still featured the same PowerTune technology from the previous graphics cards. In 2015, AMD introduced their next high-end GPU, codenamed Fiji, and the Radeon 9 Fury X graphics card as the flagship product. In terms of power management, the Fury X improved from the previous generation GPUs as it featured the voltage adaptive operation and adaptive voltage frequency scaling technologies first introduced in Carrizo. Towards the end of 2015, AMD worked on a new driver and software package. Retiring the Catalyst moniker, which had served AMD and First ATI since 2002, the new software launched on November 24, 2015, and it was called Radeon Software Crimson Edition. Fortunately for overclockers, Overdrive was still present and all overclocking knobs were still available. The successor to AMD Fiji, Polaris, was announced at CES 2016. The GPU would eventually make it to market on June 29, 2016 with the Radeon RX 480 graphics card. It's a bit fuzzy on whether Polaris was the first or second generation GPU to integrate AMD's clock stretching and adaptive voltage frequency scaling technologies. As we just learned, Fiji seems to have been the first. However, in the Polaris white paper, we read Polaris is AMD's first GPU architecture to take advantage of the advanced power management and circuit design techniques that have been developed for CPUs at AMD. A significant change for overclockers was retiring the Overdrive feature in the AMD software package. Instead, AMD offered Radeon Wattman as the toolkit for people who want to tune the performance of their graphics card. Radeon Wattman offers a wide range of overclocking tools, including performance per watt profiles, automatic overclocking, manual overclocking, graphics card monitoring, exporting and importing profiles, and power limit adjustments. Alongside this second generation Polaris, AMD launched their next GPU, Vega. AMD Vega is a 14nm GPU based on the 5th generation GCN architecture. The The GPU would eventually make it to market on August 14, 2017 in the form of the Radeon RX Vega 64 graphics card. Naturally, it inherits the AVFS and adaptive clocking technology from Polaris, but also comes with a couple of other relevant improvements. Vega also included a more powerful integrated power management controller. The new microcontroller allows for implementing more complex power control algorithms and the addition of a floating point unit, allowing for higher precision calculations. Vega also added a third clock domain for its Infinity Fabric SoC level interconnect alongside the graphics core and memory domains. The Infinity Fabric connects the graphics core to the other on-chip functions like multimedia, display, and I/O. The Vega 20 refresh consumer products and world's first 7nm GPU launched on February 7, 2019 with the Radeon 7 as the flagship product. Vega 20 is a simple die shrink of the original Vega GPU launched a year earlier. Thus, there are only minor architectural differences. However, a significant change would come to how AMD tackles the challenge of power management. As disclosed in a Linux patch note from Vega 20 onwards, the GPU will no longer use the traditional PowerPlay driver, but instead use a new SW SMU framework. A key line in the patch notes indicates that the system management unit reads the PowerPlay parameters from the vBIOS and stores the information with the system management controller. The SMC controls all power management related functions, including DPM states, clock frequency, and voltage.
While this new approach was not implemented for Vega 20, it would become implemented with the next generation of graphics cards, as will become clear in the next couple of minutes.
AMD Navi is a 7nm GPU based on a new microarchitecture called RDNA and came to market on July 7, 2019 as the Radeon RX 5700 XT graphics card. It gets a little fuzzy on the specific power management technology used in the current Navi graphics cards. We only know that there's no PowerTune on the product specification pages. Furthermore, overclocking support embedded in the new driver software package is entirely different. We now have a voltage frequency curve instead of having frequency and voltage control over specific DPM states. The voltage frequency curve enables the configuration of two distinct points, the upper limit and the lower limit. Each point can be configured with a specific frequency and voltage within arbitrary limits. Aside from the voltage frequency curve, there is also an option to increase the memory frequency and the power limit slightly. In the 2020 release of the Radeon Software Adrenaline Edition, a more general performance tuning tab replaces the Radeon Wattman. Again, the same features are still available, however, they're rearranged in a more easy to digest format.
The second generation of RDNA products and Navi 20 series GPUs launched on November 18, 2020 with the initial flagship Radeon RX 6800 XT graphics card.
It's again not very easy to cover what's changed on the GPU frequency boosting technology, as there's little to no information available from AMD. We can only highlight the slight change in the performance tuning software interface. The voltage frequency curve was exchanged for two sliders, minimum and maximum GPU frequency.